Module 10, The Chemistry of Solutions. Freezing Point Depression. Experiment 10.4. Have you ever noticed with snowy or icy conditions that in order to prevent the roads from icing up, people will pour salts or other chemicals onto the roads to break the ice down so that it won't be slippery? Well, what's going on there is a phenomenon called freezing point depression, and we're going to explore that in this lab. So the first thing we're going to do is we're going to take 2 beakers or 2 small cups and fill them with 50 milliliters of water. And this is a qualitative measurement, not a quantitative measurement, which means it doesn't have to be exactly 50 milliliters, but somewhere close to the vicinity of that. And that's 50. Okay, and then to one of these beakers, I'm going to add a 1/4 teaspoon of salt. And I want to mark the beaker that I'm putting salt into. And if you've noticed, if you have your beakers, there's these little white boxes. These white boxes are perfect for that. With pencil, you can mark that, and then it's erasable and reusable. So that's just a helpful hint for your glassware. If you're using regular glasses that don't have that, you can put a piece of tape on that if you wanted, maybe some masking tape, just so that you know that that will be your container that has the salt water solution. So I'm going to add the 1/4 teaspoon of salt and then stir that around until it dissolves. Okay, now once it's dissolved, we're going to take both of these beakers and set them in the freezer until they freeze. So I've taken both beakers out of the freezer and they've frozen to about a slushy consistency. If yours end up getting solid, just pull them out of the freezer for a couple of minutes and let them thaw partially. You want a mixture of ice and water together. I have the salt water container now, and I've put my thermometer in there to measure the temperature. Let it sit for a couple of minutes to get to that point. And I have the temperature reading now at -3 degrees Celsius. So the temperature of salt water that's frozen is -3 degrees Celsius, which is much colder than the freezing temperature of water. So now we're going to take the temperature of the slushy, just plain water without the salt. Make sure you've thoroughly rinsed off your thermometer for this next part. Now we're going to take the thermometer and put it into our ice and water mixture without salt. And you want to let it sit for just a couple of minutes so that it completely gets to the same temperature, so the temperature reading is accurate. And I'm almost there. It's going down a little bit. And after about 2 minutes to 3 minutes, our reading is 0 degrees Celsius, which is higher than the temperature of the salt water that was frozen. And so this demonstrates freezing point depression. Once you have completed experiment 10.4, we can talk more about what's going on. The experiment itself wasn't too elaborate, or even exciting for that matter, but what was going on at the molecular level was pretty cool. You know that pure water freezes at 0.00 degrees Celsius. If you have a glass of water with some ice cubes, as long as it is well stirred, the temperature will always be 0.00 degrees Celsius. But in the experiment, you should have found that the salt water solution was lower than 0 degrees Celsius. So you can make a conclusion that salt water has a lower freezing point than 0.00 degrees Celsius. And that's true for most solutions. When a solute is dissolved in a solvent, the solution always has a lower freezing point than the pure solvent. The experiment had you use a solvent of water, which has a known freezing point of 0.00 degrees Celsius. But you created a solution of salt water by adding salt to the second beaker. And that solution had a lower point at which it froze. We call this phenomenon freezing point depression. If you live in areas where it snows in the winter, you may have seen trucks spreading salts onto icy roads and driveways. That's because the salt is a solute that mixes with the water. It lowers the point at which water freezes, or the freezing point of water. That means the weather has to get a lot cooler for that saltwater solution to freeze. Therefore, the roads aren't as likely to ice up. Chemistry saves lives. Now let's talk about why solutes reduce freezing points of solvents. To do this, we need to look at what's going on when a liquid freezes in the first place. In the liquid phase, molecules have a good amount of energy and can move all around the container they're in.
To change to a solid state, the molecules have to slow down so that they don't move around anymore. They just vibrate back and forth. The only way they can slow down like this is if we take energy away from them. And that's what is happening when we cool a substance down. We are removing energy from it. So as a substance cools down, the molecules lose energy and slow down. When they lose enough energy, they stop moving around completely. This is when the liquid becomes a solid. Now, when a solute is dissolved in a solvent, the solute molecules or ions also move around the solution, right? The molecules of the solvent are attracted to the molecules or ions of the solute, following them around the solution, and vice versa. So this attraction makes the solute and solvent molecules move around more. That's why more energy needs to be removed in order to slow them down. And that means lowering the temperature even more. We can sum this up by saying that the mutual attraction of solute and solvent tends to add energy to the molecules in the solution. And because freezing means we have to remove energy from the molecules in a liquid, the freezing temperature of a solution has to be lower than the freezing temperature of the solvent by itself. This should give you a better understanding of freezing point depression. Now we can take that concept and add some concrete values to it. We can actually predict exactly how much a freezing point of a solvent is lowered when it has a solute dissolved into it. And this is why we need to know molality. Look at this interesting equation. It's equation 10.2 in your text. When a solute is dissolved into a solvent, the change in the freezing point can be found using it. The triangle is a capital Greek letter delta. When you see that letter in science, it refers to a change in something. Delta T here means a change in temperature. The lowercase I stands for the number of ions or molecules that the solute splits up into when it dissolves. And the lowercase m is the molality of the solution, telling you how many moles of solute per kilogram of solvent there are. Now, what about the capital K sub F? That refers to a constant called the freezing point depression constant. This is a physical constant that is completely dependent on the chemical nature of the solvent. So each solvent has its own specific value for K sub F. Water has a K sub F of 1.86 degrees Celsius per molality. Acetic acid has a K sub F of 3.90 degrees Celsius per molality. To understand the weird units of K sub F, let's look at the units of the freezing point depression equation. We should expect delta T to have temperature units of Celsius because it refers to a change in temperature. The I doesn't have any units because it just lets us know how many pieces the solvent breaks up into. And M refers to moles per kilogram. Our constant is degrees Celsius per molality, which is degrees Celsius per moles per kilogram, or degrees Celsius kilogram per mole. So when we cancel out like units that are in the numerator and the denominator, we get degrees Celsius, right? Well, let's walk through a problem together. When 15.0 grams of sodium chloride are added to 100.0 grams of water, what is the change in the water's freezing point? Given the freezing point depression constant of water equals 1.86 degrees Celsius per molality. We're asked to find the change in water's freezing point, or the delta T. So we need to use the freezing point depression equation. We're given the freezing point depression constant for water, which is our K sub F. We need to figure out I and M. Molality can be calculated by finding the moles of sodium chloride per kilograms of water. We can find moles of sodium chloride by taking the 15.0 grams given and multiplying it by the conversion relationship of 58.5 grams of sodium chloride equals 1 mole of sodium chloride. Canceling out grams sodium chloride, we get 0.256 moles sodium chloride. That value goes here. We can convert 100.0 grams water to 0.1000 kilograms of water, which is our solvent. Now we can calculate molality as 0.256 moles sodium chloride divided by 0.1000 kilograms water, or 2.56 molal. That is our M value, which we can put here. For I, we need to look at our solute. Sodium chloride is an ionic molecule, so we need to figure out how many ions it will split into when it dissolves. Sodium chloride becomes a sodium 1 plus ion and a chloride 1 minus ion. So each sodium chloride molecule will separate into two components. Our I value is 2. Now we can multiply through the equation to get a change in temperature, or delta T, of negative 9.52 degrees Celsius. Note that because our I value is an exact number, we don't consider it when we are determining significant figures. Exactly 2 ions are produced when sodium chloride dissolves. What does this result mean? Because the answer has a negative sign, it means that the freezing point will be lowered by 9.52 degrees Celsius. How about this one? What's the freezing point of a solution that is made by mixing 2.5 grams of aluminum nitrate, AlNO3, in 150.0 grams of water, given the freezing point depression constant of water equals 1.86 degrees Celsius per molality? This is another freezing point depression problem, so we need to use our new equation. We need the K sub F, I, and M values. We're given the freezing point depression constant for water, our K sub F. We can find the other two. For molality, we need to know moles of aluminum nitrate and kilograms of water. For moles aluminum nitrate, we can take our given grams of that solute, 2.5 grams, and multiply it by our conversion relationship of 213.0 grams aluminum nitrate equals 1 mole aluminum nitrate. Remember, we can get that relationship by finding the molecular weight of a single molecule. Multiplying through, we get 0.012 moles aluminum nitrate. Let's put that here. We can convert 150.0 grams water to 0.1500 kilograms. To calculate molality, we divide 0.012 moles aluminum nitrate by the 0.1500 kilograms of water, and we get 0.080 mole. We have our value for M. For I, we need to look at our solute to see how it dissolves. It is an ionic compound, so it will divide up into ions. How many ions? Well, we have 1 aluminum 3 positive ion and 3 nitrate 1 minus polyatomic ions. I know this because of the 3 here. How many total ions will 1 molecule of aluminum nitrate separate into? 4. I can put that number here. Multiplying through equation 10.2, we get negative 0.60 degrees Celsius. What was our problem asking us? Well, it wants us to find the freezing point of this solution. We found the change in freezing point. That means that the freezing point of the solvent was lowered by 0.60 degrees Celsius. You know the freezing point of water is 0.00 degrees Celsius. So the freezing point of this solution will be that number less 0.60 degrees Celsius, or negative 0.60 degrees Celsius. Okay, let's do one more to make sure you're following this. What's the freezing point of a solution that is made by dissolving 100.0 grams of table sugar, or C12H22O11, into 950 grams of water, given the freezing point depression constant of water equals 1.86 degrees Celsius per molality? Well, just like the earlier problems, we need to find molality of the solution and our I value. To find moles of sugar, we can take our given value of 100.0 grams sugar and multiply it by the conversion relationship of 342.2 grams sugar equals 1 mole sugar. That gives us 0.2922 moles sugar. Let's put that number here. We can convert the grams of water to kilograms by multiplying 950 grams by the conversion relationship of 1,000 grams equals 1 kilogram. And we get 0.95 kilograms water. Put that number here. Now molality is then 0.2922 moles sugar divided by 0.95 kilograms water, or 0.31 mole. We can put that value into our freezing point depression equation. Now we just need our I value. Look at sugar to see how this molecule will dissolve. This is not an ionic molecule because there are no metals in it. That means that it won't separate into ions. It will dissolve into single sugar molecules. That means the I equals 1. We can plug that value into equation 10.2 and we get negative 0.58 degrees Celsius. We are asked for the freezing point of the solution, so we know that it will have a freezing point that is 0.58 degrees Celsius lower than the freezing point of the solvent. The solvent is water, which has a freezing point of 0.00 degrees Celsius. So the freezing point of this sugar solution is negative 0.58 degrees Celsius. Now there's one final thing I need to address before we leave this section. Your book refers to the point where a liquid becomes a solid as the freezing point. But if you think about it, we could also call this the melting point. Think about water. It freezes at 0.00 degrees Celsius and becomes a solid. But at what temperature does solid water become liquid water? The same temperature, right? If we heat up solid water, the moment it goes to the tiniest point above that number, it becomes liquid. The moment it goes the tiniest point below that number, it becomes a solid. So any substance will freeze at the same temperature at which it melts. We use the terms freezing point or melting point depending on which direction we're going. So some sources will use freezing point for this concept, and other sources will use melting point. Just know that they are really the same thing.